Journey down the rabbit hole with Joe Kenyock and Luke in control. Every twist and turn we dig for the gold, holding power accountable, brave and bold. Hey, don't get none on you, just stay awake. Hey, join the ride with us for the truth's sake. So gear up, my friends, it's gonna be wild. With Joe Slick leading, you'll be beguiled. The truth is waiting, don't miss the call. Like Joe says, rise up, we'll break down the wall.
Good morning, good morning, good morning. It's 8:17 here in the West, and we are recording this video for the YouTube audience. And I was looking up an interesting article that I came across regarding the pulse of the Earth. Maybe I can look it up that way. Pulse of the Earth. I think it's 24-second pulse of the Earth. The Earth emits a faint rhythmic seismic pulse or a heartbeat approximately every 26 seconds. This was discovered in the 1960s. This consistent microsm originates in the Gulf of Guyana and is likely caused by ocean waves interacting with the continent shelf or by activity of the volcano Sao Tome Island. That's wild. Key aspects of this 26-second pulse, known as discovery in nature, known as the microsism. This faint tremor was first documented by Jack Oliver in the 1960s as low-frequency vibration that is consistent and undetectable by humans without seismic equipment. The source has been narrowed down to the Gulf of Guyana, part of the southern equatorial Atlantic Ocean. Proposed causes are ocean waves hitting it, volcanic activity, including researcher Ying GIA, proposed that the pulse originates from ASO-like volcano on the island of Sao Tome, similar to the tremors of the ASO volcano in Japan. Consistency, the pulse is consistent and has been recorded consistently for over 60 years. Not a threat. Despite the ominous name, the pulse is naturally occurring, harmless phenomena that help researchers study the planet's internal processes. This is wild. It is an article that came out. Even Silky's got something to say on it. If you watch her, like myself, watch her with a, like you're eating fish. You take out all the bones. Earth. Let me see if that's the article. Yeah. It's pretty cool idea there. The Gulf of Guyana, near Bight of Bonny off West Africa. Yet the decades research scientists will still can't agree on why it happens. Some theories suggest that the result of powerful ocean waves pounding the continental shelf. The Gulf of Guyana. Let's kind of look that up here. Near Bight of Bonny. Let's go ahead and put on a G. Where the heck did it go? All right. Well, couldn't figure it out. All right. Bight of Benny. All right. So this is really interesting. All right. Um, Sao Tome is a series of volcanoes that go into the armpit of South Africa. Okay. Let me go ahead and drop that out here for you and then put this one in here. There you go. All right. Here's Sao Tome. Here's a series of volcanoes that come off of St. Helena, the Ascension Island of De Kahuna, right? Right? They come all the way into Sao Tome. And I think we did a rabbit hole one time where we saw activity go all the way across Africa, you know, and that. Here's the Gulf of Guyana. Let me, you know, ding your brain just a little bit. Wasn't there an anomaly that when we looked up wind, they may have removed this ability. When we looked at windy, right, and we would see waves of energy come from the Antarctic, move right up the coast of Africa into that location. Wasn't that happening? Oh, a little bit ago. You know, it was maybe a year and a half ago, and it was such a strange anomaly that nobody couldn't. No, it was seal. It was on windy, and it was waves, not wind speed, but waves, and we would see waves like this push straight up, and scientists couldn't understand it, and so I think they changed some of the doohickeys here. I wonder if it's related. That's what I was trying to get at. You can see the offshore waves that move up into fresh water up in here um, from the sea. But and the Atlantic is more salty than the Pacific, so kind of figure that kind of weird stuff too. And what is salt? Isn't I wonder. I'm going to ask the question first. Is salinity salt or salinity is not inherently magnetic, but it is electromagnetic in behavior because dissolved salt ions create highly conductive, electrically active solutions. Salinity is frequently measured and mapped using electromagnetic induction, or EMI, sensors that detect how salt ions conduct electricity. The conductivity based of salinity is measured by how easily electric current flows through a solution. Higher salinity increases electroconductivity. Electromagnetic mapping, such as EM38 and EM31, generate magnetic fields to induce electrical currents in the soil or water mapping, salinity based on conductivity. Interaction with water, dissolved salts like NaCl dissociate into charged ions Na plus and Cl minus that interact with electromagnetic fields. Electromagnetic sensors, these sensors are preferred over direct contact probes for measuring soil and ocean salinity because they are not invasive and efficient. Ocean tides and magnetic fields. If you would like to discover a little bit about that, I'm going to drop a link in here. That will kind of give you a little understanding into seawater and is an electroconductor and therefore interacts with the magnetic field of our planet. As the tides cycle around the ocean basins, the ocean water essentially tries to pull the geomagnetic field along these lines. Because the salt water is good but not great conductor, the interaction is relatively weak. Scientists at NASA Goddard Space Flight Center are developing improved methods to isolate the signal from the ocean tides that use information to determine the heat content of the ocean. Yeah. Memory of a lifetime. Okay. There is a video here. I don't know that it's scientific video. Okay.
Earth, spinning through the solar system, proudly bearing a majestic magnetic field emanating deep within its molten metallic core. The ever-changing field is full of fluctuations from many sources. Satellites observing these oscillations let scientists identify individual sources creating the magnetic field. One such source is the motion of the ocean. As the ocean flows, the field lines feel a pull and are dragged along a little. The back and forth of the tides cause a small wiggle in the magnetic field. Scientists have isolated this one small oceanic signal, measuring it from a satellite orbiting high above our spinning globe.
There you go. The reason I bring that up is often we're talking about how the tides are working, and what was happening here off of Africa was a powerful tide that was going north, and it was a strange anomaly. What else is it? Yeah, a powerful, swift ocean current known as the Agulhas current flows southward along the east coast of South Africa. East coast, that would be this one. And swells, it generates massive swells and treacherous, dangerous sea conditions. The biggest swell of the year so far for J-Bay yesterday. So it is being watched. Surfers watch it quite often, so that's not going to help us. Anomaly. I don't know. I mean, I didn't know if I spelled it right. I think I did. Let's see. Yeah, huge anomaly near Africa. It's a gravitational anomaly. And there's a reason I'm bringing that up so that I can...
How wonderful person this is, Anton. And
Sorry about that. That's Anton Petrov. He has a show about that exact same thing on YouTube here. And I'm not going to play it because I don't want to get in trouble with YouTube.
I find it...
And then, man, I got to just kill the music here. There we go. There's also another lady who's a scientist on YouTube, Sabine Hossenfelder, and she's talking about the same strange anomaly that was taking place here last year. Now, the things that in common are the salinity of the Atlantic, the motion of waves, right? The strange anomaly that was taking place off of Africa from 2006 to 2008, I guess. But she's got a really interesting article, which we made play it after the fact. I'm trying to see a picture to show with you. There's a reason why I'm bringing that up too. I keep saying that, and just get to it, son. It's hard to deal with, man. Yeah, here's Newsweek even has an article about it. Happened in May of 2024. The southern Atlantic wave anomaly deepens. Copy, and I'll put that in there. So, I thought it was pretty interesting. Weather mapping systems have yet to again to capture what some have claimed is a wave anomaly in the off the coast of southern Africa, causing speculation online about a dark blob. See if I can see an image of it for you. Yeah, for the second time in a month. Okay, yeah. Let me see. All right, so back that up just a hair. I'm going to get the picture of it. All right. God bless it. I missed it. All right, here we go. God bless it. I missed it again. It's quick, man. Yeah, Vendusky is what had it. God bless it. Just almost had it. 1, 2. All right. So here's what it looked like. All right. So very strange. It was right here. It moved off of this coast and came north. All right, on Vendusky. Here's this southern wave anomaly right there. Yeah, okay, I got it all off. All right, whatever. What the frack? Man, am I trying to do this again? Let's see if it works. That item right there. And it took me a minute to get it, but it is on the internet. It happened in 2024. And the pulse that we're talking about here in it's a mystery, right off the coast of Africa in the Atlantic, off the coast of Africa, right? So it touches the magnetics of our planet and the salinity of the ocean and the L shells and all of that. So when we go in and we start to talk about space weather, right? And this is how me summarizing it up. It's evidence of the component. And I say the component with a capital C because we don't know what to really call it yet, but there's so many different studies in specific areas that do have an overlapping trend, so to speak, and they talk about how our Earth functions, and studying Earth science, and it's basically we're an Earth science site. We don't just study Earth science, but we also hit the headlines and what's going on in the world around us, because we too are part of the system, the greater large system. See, there are people who are looking for the magic bullet, so to speak, talking about, how this is how earthquakes happen, or the like, trying to forecast earthquakes. I think we can get kind of close, 60-70% likelihood to say this is an area of interest. I don't believe we can forecast an earthquake, so to speak. Now, I've said, there's going to be an earthquake, and it's happened, right? Just because I thought there was a place of interest and it was happening. Was it exactly the same size that I thought? No. Did it happen right at the very spot I saw? within a couple 100 miles, yeah. Does that make me special? No, it just makes me very freaking lucky. I was able to see the trends, what happened. We can also see throughout history a progression of earthquakes that go along the plate boundaries, that sometimes traverse across the middle of the plate, which throws a lot of people off. And when we start to see these waves of energy working across, we can say, okay, this area is a place of interest. Now, sometimes it's like from Mexico all the way to Alaska. Oh, well, that's a long damn way. Yeah, it is. 1,800 kilometers, right? Or something like that. Some crazy number. Maybe 2,000 kilometers. So it's not like, oh, I was right on. Well, what I saw, or what somebody else would say, is that they would see the trend of the North American plate moving away from the Atlantic ridge. You know, we'd see movement along the Caribbean plate. We would see the Cocos plate move, the Nazca plate move, the Pacific plate move, the North American plate move. And then on the opposite side, the western side, where we see the North American, which goes all the way to Tokyo. And then we see the Eurasian plate move. We'd see the Philippine plate move. We'd see all the little micro plates inside the maritime continent of Indonesia and Malaysia and Micronesia and all of those. And then we'd see it also on the Australian plate, and it's buffeting area where New Zealand located, and Fiji and Vanuatu and the Solomon Islands all the way over to PNG. We would see those kind of trends work their way through. And we can watch earthquakes, large earthquakes, move along in areas where we can say, hey, wait a minute, there seems to be a trend here. And we can see in a smaller microcosm, like moving along electromagnetic lines, which we term lineaments. Along these lineaments lines, so they're electromagnetically visualized, and whether or not they're induced or deduced, for that matter, we can see trends. And when an earthquake happens in one location, we can see that it emanates out waves, a P wave, an S wave, and also another, an R wave, whatever. And how it affects the plates around the world, and how it bounces back and stays in that the greater planet, so to speak. It rings the bell of the planet. And if we were to look on all the seismometers across the world, we would see how these interactions are taking place. Like on the globe, you see in the top left-hand side of your screen, those are the latest earthquakes in the last 2 days, and those are 4.5 and above. And we can see in the there's not a whole lot along the African side or the Atlantic margin, the mid-Atlantic ridge, but we can start to see where there is along the Eastern Pacific side, which is South America, up into Central America, and then up into North America and into Alaska, and they're about almost in a straight line on a planet. We would say that maybe there's some sort of lineament controlled along that multiple plate boundaries. It traverses multiple plates. Also, you start to see Fiji now coming into view, and then across over to Vanuatu, then up through Indonesia, up into the Philippines, and up into Japan. And then there's a big gap, and then now we're starting to see something up in China. Now, those Chinese ones can come up and over the top from Japan and through Russia, coming back down, working their way through all the stands, and then into the ladies that I call them. Iranistan and Kazakhstan, all that, moving over to Georgia those more feminine type names, and then into Turkey and then across Europe. We can see a progression of earthquakes and a seismic activity. But if we're only looking at that, we don't really see the larger picture. And my supposition is that the mechanism of the planet is influenced, there's evidence of a mechanism, and one of its influence is the electromagnetic energy. Also, however strong or weak, it's kind of relative. Could be positive or negative ions coming from the sun. Often, many people look at, say, a geomagnetic storm that just took place. Man, there's going to be an earthquake. And a lot of times it happens. And when we look at, the Earth absorbing, like in this area right here, a small flare, it was absorbed right here. Well, why was it there and not over there? Well, because of the time of day or night thereof, mainly day because the sun is on that side of the planet, right? So we'd go in here and we'd say, well, right there's where the sun is. Well, in this region, well, that's where it is, right? So there's more light energy from the flare hitting that place. Then we say, well, okay, let's go ahead and look at the sun, right? And we can look at the 131 angstroms here. We can see there's a series of sunspots, more activity coming up on this end, right? Now, in the geomagnetic sense, we would see not a whole lot, because we'd have to go back and look at this, right? These are plasma waves that have left the sun, and it takes time because the sun's spinning and the earth is spinning to get to our planet. That's why we see this kind of spiral, right? And we measure the amounts of density per cubic centimeter of protons, right? Positive or negative protons that hit our planet. And when they do, there's an increase, and that's charging our planets, how some of us would say. And if we put this in motion, you would see how this, like, it happened here, and by the time it got to us, because we're, a long ways away, from the sun, it takes a minute before it gets here, usually about 2 or 3 days. Okay, I'm not sure how it applies. Keep that. Tell me a little bit more, Tim, because that's an interesting case there. On the bottom, we have solar wind. Now, solar wind comes out of energetic particles from the sun. I'm not sure if they're positive or negative, but the plasma is ions that affect our planet. Well, how do we look at that? And this is the predictive sense. So scientists are watching the sun, and how when the sun releases energy, you see a little more energy has hit our planet right here. This is our planet, a representation of a side view. You can see one big one went north of us, and north being relative to the position of the Earth. And it didn't affect us. And then we just went through one, right? And you can see how it peaks here on the 30th, which is tomorrow, right? So that one never affected us, but these ones do. Well, what does that mean? And then we look on the bottom one. This is solar wind, right? An immense amount of solar wind is emanating from the sun, right? Probably through a coronal hole, which is a less an atmospheric part of the sun, which we'll look at here in a minute. That's not affecting us here this week. And remember, the sun is rotating, the earth is rotating. The earth it's more relative for the earth, but the earth is so spinning. So, by the time it continues by us, on a 3-day journey here, you see a 29 through the 1st. Well, the whole earth is spun 3 times, so it affected the entire planet. And then when we look at the ground magnetics of our Earth, these are magnetic perturbations over North America, right? And this is over the entire Earth. And this is a 4-hour window, right? We know right now the sun is moving, it up and over Brazil in this time frame. So we're seeing the auroras up high, but also on the ground, the effects of the sun, right? So we're seeing, we're trying to visualize the whole mechanism of how our planet responds to the sun. And so we're watching with these tools. And if I played this one as I download this video, you'll see bright spots happen where the sun releases an immense amount of energy, sometimes millions of Kelvin heat. Like that was a blast that just took place. Whoa. These are popping away. I've never seen that. It affected our satellite there, I guess. A couple of these are popping off. As we work through. That was really interesting. I'm trying to get to a bright spot, like right there. That is a, we would say probably a C something or other, C flare. That is not, Earth is directed like, here's the center of the Earth right over here, right? But this is a satellite looking at it, so it might be off to the right or left, depending on where the GOES 19 is located at this period of time. Looking at the sun directly and using filters to look at the sun, and you can see this explosion off the sun emanating light radiation from the sun, and that radiation can be positive or negative. So in looking at this type of thing, I can push play on this, say, well, it hit our planet in this region. Like here's one that hit the planet in that region, right? And the stronger, the more, red colors it would be. The weaker would be in more of the purple colors, and the greens would be in the middle, right? So when we start to see these things, like there's a little more blue right there, maybe another C flare, right? There just isn't very many right this minute strong information that's hitting our planet from the sun. And if I did, minus 6 hours back, what just happened here? Yeah, you'd see. So if I subtracted 6 hours, that's where the sun was 6 hours ago. So when we're looking on that doohickey, you'd see that other page. You would see, well, okay, it was over here 12 hours ago, right? So it affected over here, but by the time we wake up here in America, the sun's over here, So we can look back in time and say, okay, well, was the sun active in that time period? Because it's all being recorded. And is there a factor where this irradiating light radiation emanating from the sun, does it affect our planet in some way? Maybe not in a B or a C flare, but often X flares affect our planet. And case in point, the Carrington event that happened in mid 1800s, 1855 or 1857 or something, or 18 somewhere. I don't remember the Carrington event. What date that took place? I'll look that up. Carrington event. Just so you know. I mean, 1859, September 2. We've had, that was an X 32 or something flare that the sun emanated from it. Let me see. What they say? The largest geomagnetic storms recorded ground-based magnetometers. Estimate storm strength range from 0.8 to 1.75 Tesla. That's magnetic flux density. A lot of big terms, right? It took 17.6 hours to hit the Earth from the sun. A coronal mass ejection, which is a significant amount of plasma that the sun's corona bursts out of the heliosphere. And sometimes they're associated with flares, sometimes they're not. So that's, part of it all. What did they say it was? 1.75 Tesla. But what it did was it affected our planet during that times that it actually hit the Earth, and that energy went all the way to the ground in some spots. And how we know that is because telegraph lines caught on fire. Some were overwhelmed, and there were auroras, the aurora borealis, that normally, if you're in my area here in Arizona, we don't really see, but we can at certain times, like we have this year, based on that coronal mass ejection. That Cuba saw it. Way down south into Cuba, Hawaii saw it, Queensland, China and Japan, New Zealand, and even Colombia, near the equator, equator, saw the auroras during that geomagnetic storm. So, I mean, let me see what the Carrington X, what? I wanted to tell you what X was. Thought it was like an X32, which is a massive amount. If that Carrington event took place today, long-term global power grid would collapse. It'd destroy thousands of satellites. The internet wouldn't be here anymore. GPS would fall out of the sky. And communication systems wouldn't work for weeks, months, maybe even a year. It's just hard to tell. What would we say? It happened at 1859 around 11 a.m. It happens about every 500 years. A storm half that intensity happens every 50 years. We've had that happen in 1989. Strong solar flares. Let me see what X value was. Oh, an X, what? Some studies suggest that it's an X105 plus 41 minus 24. So they couldn't tell. An X50, 40 to X50 is the best understanding. Scientists updated scientific estimate in monthly notices of the Royal Astronomical Society suggest it was an X105, okay, which is freaking crazy. Let me see if I can give you that paper. Yeah, all right. So here's the. Why do I say that that's crazy? Well, I think we're still on. All right. There's the article. It says the Carrington event is suggested not X50 but X105. Only because they've noticed that we've had X35s like I think in 1989. The first reported optical observation of the Carrington 859 was accompanied by the earliest reported case of solar flares effects, SFEs, in 1861. The SFE phenomenon, also termed a magnetic crochet or crochet, remains useful as a proxy for solar X-ray and extreme ultraviolet emissions, or EUVs. And the Carrington event certainly was a powerful flare, and it has caught the public imagination as embodiment of the super flare that some were suggesting it was, who said this arbitrarily at an event total energy of 10 to the 33, capable of causing great damage to human society, by one particular article. And let me see if I could try to get that for you. Yeah, here's a reference. So if you want to see that reference and look it up, I'll put that in chat for you as well. The radioscope events discovered in an ancient tree rings that ice core suggest occasionally solar sources of energetic particles greatly outstrip even the huge solar eruptions such as that of the flare. Solar 1956 by Parker and Simpson, and by a few others. This event had a greatest high energy particle fluence recorded since such observations began early in 1940s. The Carrington event as a superflare notably lies between the family of eruptive solar flares and perhaps physically different historical events inferred from radioscoping records from stellar photometry. So what they've noticed that these solar flares and geomagnetic storms affect our planet. And again, that's kind of what I'm trying to get at with what I'm saying here. There's a reason why we look at solar stuff and interplanetary effects upon our planet. And then we look at ground magnetics, right, which we already talked briefly about. Flare absorptions, which we briefly talked about. And then this graphic image of how our magnetosphere, which is our electromagnetic protector around our planet that protects us from the greatest rays from the sun and other entities. And we see the velocity of the wind in this top one. We see the density of the protons, the hydrogen and helium ions that either positive or negative affect our planet and when it buffets our planet. And then you see the pressure applied upon our magnetosphere. Again, these are all graphical representations. And when we look at these things, we say, okay, well, there's not a whole lot of wind right here. The darker blue is a little more protons, coming at us. And if I pushed play, it would record like maybe a 4-hour window, and you'd see there's a little buffet of our magnetosphere and how our our core of our planet has like a toroid. It's not just a circle. it moves, and it's all over the place. And then we would see how it affects, waves of energy effects, and kind of like a flag, how it's flowing. And these are the waves and the electromagnetic I would say lines, but they're more areas of our electromagnetic energy where they're stronger or weaker, for that matter, get kind of buffeted and move a little bit. Now, we've seen super strong densities where all this white is like almost all gone, and all the blue. Does that mean our planet's being destroyed? No, it just means a lot of plasma is coming from the sun. And then we look at this dense, or the pressure here upon our planet. Here's our Bowflex. I call it a Bowflex. Looking at north to south, and this is from the from looking up from the top of our planet all the way through the bottom, right? And where the sun is, this Earth is rotating. You'll see that on the backside there's a little bit of pressure because of what's flowing. The L shells are flowing, and then they kind of break off, so to speak, and then reappear, and the energy kind of comes back as a backflash on our planet. Looking at that, and then I look at the here's the magnetopause, another graphical representation. Right here is where it's being buffeted, and this is, again, is by the minute. We can see that the average protons per cubic centimeter here registering. The BZ is kind of like more energy in the north or the south, and when it stays like negative 10 or positive 10, that's still kind of in the middle. All right, we can look at another site that would take a look at the BZ here. It's primarily in the south, so there's a lot more energy. Now our planet is like on one plane. Other planets are on a different plane, but they all rotate around the sun, right, in a corkscrew, and as the sun is corkscrewing through the universe as well. So there's times when north or south is a little more exposed, and it depends on the seasons as well. And so we have to take a lot into effect in interpreting the BZ, so to speak. But the BZ is right here, right? And then it says the standoff distance of our Bowflex, the strength of one of the areas where our magnetic protector is the strongest. And you can see it buffets, it bounces in and out depending on how many protons and how much solar wind speed per kilometer per second, 310 right this minute on this one. And then we take a look at that and say, okay, the energy from the sun, which is, it's all invisible to the naked eye, to us, but not to instruments which we've created to record these things. And you'll see the standoff distance. These are the area where all our main satellites are, right? And we've seen this Bowflex get into that area, and those satellites get damaged. And you can see the dynamic pressure right here on the bottom. So when I was looking here, the dynamic pressure, that is pretty low. It's below 1, and they show you the red starts to about 1.5 and then 0, right? So there's not a whole lot of magnetic pressure upon our planet at this point in time. Why do I try to explain all these different things? Because they're all part of the mechanism of our planet that, and there's a lot other ones, just these ones I'm able to tell you now, that create and are part of plate movement. When let me see here. I don't even have it on here right now. Cool. Here we go. I need to put it. Well, I can do it this way. Boom, 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 boom. Come here. All right, let's see if you can see that. Boom, boom, boom. Okay, cool. What was I doing? Okay. We have just the graphical representation of North America, right? You know, so comes out of Alaska, down. You got this one, comes down. You got that little one, it comes down, and then you got the Gulf of Mexico, and then you got South America. Then we have the one out here, comes off the coast, right? Comes down. Oops, that's not even a good representation. Sorry. Comes down, and then here we are, Florida, right? Gulf of America, and then out that way. Actually, this will come in here, and then out that way. Oh, just trying to do it too fast, I guess. And then back to it, and you'll see it then. It's kind of down the eastern seaboard. Out here you got Greenland, then you got up here you got Iceland, so to speak. This plate is moving in that kind of direction. You got the Caribbean, which is out here. It's moving in that kind of direction. The Pacific plate is moving in that direction. And you got the arc of the islands. And Hawaii's out here. And then you can see that the chain of islands are this way toward Midway. And then all of a sudden you can see the change in the imperial fault or imperial seamount chain go north. Something happened about 40 million years ago, 40 to 45, to change this direction in the whole entire Pacific. All right? So something they believe happened either off of Kamchatka or Japan or the Philippines or Indonesia or PNG or Vanuatu or Fiji or down here in New Zealand. So something happened on the west to make this change here to this change here. Something happened out there. It changed the entire area. Well, we study often in our classes due to the great opportunity that Nick Zentner gives us. And yes, I have asked him to use his material as he so graciously has granted. He's a wonderful teacher, and he's excited about geology as well as us. He's been a teacher for more than 20 years. And we've learned quite a bit over the past 6 years of his teachings, that he's able to do it online due to COVID. One of the next other blessings of COVID, that took place. So all of these movements, see, the North American plate, I can show you probably easiest if I use the USGS image. And right here, you can see, wow, we got some Alamo, Nevada popping off. Oh yeah, check that out, man. We have a 4.4, and then right after that, we have a 3.2. Well, we'll talk about that in just a minute. And then we have that other one that's been going off, Silver Springs 3.3. So Nevada's been super, super busy. I think it's the second state beyond California that is that busy, by the way. But you can see these red lines. These are the plate boundaries all the way around the world. And the North American plate, comes out of Svalbard up here on the right, comes down through Iceland, down the mid-Atlantic ridge, and then breaks off somewhere out here, which is not really known where that is. And then the Caribbean plate down here in the middle, and then the Cocos plate, the Nazca plate, and the Pacific plate. And all of these move at a certain kind of direction and speed And if we looked at this, this representation, graphical representation, helps us see the average speed of the plates, right? These are all in millimeters per year. So, off of North America, it's moving at 70, basically 76 off of Baja California. The Gulf of America is moving at 26 at almost the same angle as North America. Parts of North America are moving due south, though, they found, and in parts of it are actually moving northeast, because this small little plate right here. And there's microplates in here. Like all of the maritime continent here is full of microplates. And they all move at a certain direction. They all talk to us, and this graphical representation helps us understand how the plates move and how that energy moves across our planet. And these are just several different ways where we are talking about the mechanism of how our planet works. And it's not all inclusive. This is only, scratching the surface, so to speak. So again, the idea behind anybody forecasting earthquakes and saying, oh yeah, there's going to be an earthquake here, that's why they 99% miss it, right? Because they're forecasting, 99% is going to be here, and it doesn't happen. Why? Because nobody can really forecast earthquakes. What we can say is, in this, even the USGS says California has a 70% chance in the next 50 years of getting a 7 along the San Andreas, or even an 8 or a 9, and a 9 up in the Cascades, right? The Cascade Range, which is off this blue line here, with that subduction. That means this portion of the plate here is going underneath North America, or North America is riding over the top, making this Juan de Fuca plate disappear. And it will. It'll force it underneath. And that's why we have the volcanoes and how they're created. And you learn all this stuff by studying, and you learn this stuff by other teachers and the like. And then you start to say, wow, this is kind of overwhelming, and it's kind of boring to me. But it's really not when you start to grasp all the different areas of the mechanism. And understanding the mechanism and its pieces doesn't guarantee you the ability to see what the hell is happening on the earth. What it does is it shows an area of interest. And that's why scientists say there's this percentage chance and a that percentage chance of these things happening. And when they don't happen, they're like going, well, we don't know what to tell you. The Coulomb stress of rocks, and how, how you can take a dirt clod and you can squeeze it, and sometimes you break it and sometimes you can't. Just like a granite stone is the same thing. How much pressure does it take to break that rock in your hand? Or can you even do it? Put it under a press and maybe you can crush it, right? So it's that pressure, the Coulomb stress, to break rock. That's part of the minute details of this movement happening at a 21 up here in the Great Lakes millimeters a year, and how 24 down here through New Mexico, Arizona, Nevada, into or New Mexico, Arizona, moving into California, and how the Pacific Plate, which is moving in a different direction, and how that pressure is contained inside the Gorda, California, Nevada microplate here, and how it functions and how it works, and it's along the San Andreas, So it's putting all these things together, and in the many other things that it would take to say, yeah, I'm forecasting an earthquake here. Some things are visually, some things are mechanically, some things are are physical. So yeah, so like rock is physical, right? The mechanical of the movement of the plates, creating the breaking of the rocks and I mean, we when we look at things like where is it? I don't think it's this one, is it? I think it's this one. Sorry. When I look at earthquakes here, right, off the offshore Honshu, Japan, right, we can look. It's looking up the data now. This is the earthquake signal through the whole planet. That the instruments that we use, like seismometers and seismeters, we'll take a look at how it affects and how it translates all the way to Texas here, right? So a big 7.4 that happened. What was the date on it? 4/20, right? Not too long ago, about 9 days ago, right? So if I push on this here, and they say this is the distance it came over here. But take a listen to this and be careful. This will hurt your ears, so monitor that. It's a 22-second recording of the rocks breaking in Japan that were heard in central Texas. I'll play it again. Right? You ready? Now listen to the depths. There it is. It's really, really deep. So what we heard was the initial P wave break. And we're listening to the P wave. That's a boom, right? Super deep, right? Is a 7.4. The depth was 35 kilometers. And so it was below the land mass. It was, the oceans are only like 10 to 15 kilometers in thick. So it was the plate that was subducting underneath the Japan plate, right? The North American plate for that. The Pacific diving underneath Japan, lifting up or pulling down Japan for that matter. There's a lot of dynamics there. And so when that initial boom, right, it took, 22 seconds for the S wave, which is the surface wave, to reach central Texas. And that's what we're hearing is that right there. That boom. Now a 7.4 is probably a rip along a fault or a subduction zone for that matter that is several miles long. So I don't know the totality of that earthquake yet. Scientists have it, but that sound is part of what's happening, the frequency. These are all, up and downs, right? This is the frequency, and you can tell it's pretty scattered. And then the S wave happens, it's much larger. Generally what destroys buildings is the S wave, not the P wave, but because they're larger and they carry an incredible amount of energy. You can see when the waves happen on the surface when an earthquake happens. It's quite amazing and alarming for that matter. But all of that is to say that the frequency of our planet having that 26-second vibration out in the middle of nowhere, and then coupled with the waves, the oceanic waves, and the anomalies that take place. Anomaly is something different other than normal. The solar energy that pops off the sun, how it affects our planet, whether it be pressure or proton density or lack thereof, solar wind, so to speak, and how we can measure each of these things, and then looking at earthquakes and the frequency of earthquakes that are happening primarily along the plate boundaries. And you will see out here, they're not on a plate boundary. There's a reason for that. And then watching how these electromagnetic signatures are affected by the plate movement, by the waves on the shore. In addition, even weather events are affected by our sun, whether it's the updraft or the downdraft of dynamic pressure upon our planet. And we can see through a dirty how much rain is out here, right? And all that. We can see in the upper level atmosphere what's going on. We can see in the lower level atmosphere, the dryness area, right? The combination area where it's, in between, where that's super unstable weather, creating these massive storms. All these little tiny things put all together is the system of how our planet works. And so when we study, and I study every day, I start bringing up, saying the solar wind right now is 310 kilometers a second. The proton density is at 3.74 protons on average per cubic centimeter, right? I can tell you we've had a C2 and a C8 flare, and also 420 and 25. Here's 420 and here's 25, both in the northern hemisphere, yet the energy is still in the south, right? Depending on the angle of our planet, right? The tilt of the earth and the way it's spinning, right? And the year or the seasons that are happening. All those things got to be taken into effect on how the sun really kind of affects our planet in totality, or the strongest point, which when I showed you the absorptions, right? This is where it mainly absorbed that little C4 flare or whatever it was. The current one that happened at 1621 thereabouts, when it hit our planet. So all these things that take an effect. This is why we look at all these different aspects, because we're trying to look at what the entire mechanism, right? And there's things that we'll add and some things we've left off in all of this. And 20 and 25 have the capacity to give us strong X flares. Now, they're not near as large as the Carrington event solar sunspot. And however, does that mean these are less plausibilities? No, they can still pop off really strong flares. And having 2 days before it gets to us, the coronal mass ejection that may or may not happen is an indicator. And also, what would happen if we did get a X105, which is what they believe now the Carrington event was. Crazy stuff. We take all this in effect. The Antarctic tongues of ionization sound like alien anatomy, but they come from Earth. They're plasma rivers in our planet's ionosphere during the great geomagnetic storm of May of 24, which we saw from those 3 X flares. A dense tongue swept over Antarctica, scrambling GPS with position errors, and as large as 28 meters, meaning the GPS lost its way for about 28 meters, right? So that happening as well. That's what solar storms can do. X flares and all of it. And it's interesting. This article here, I'm going to put it in chat for you. If you on YouTube haven't come over to twitch.tv/Joe Slick Live and watch our live shows, you can join over here with a modest, $6 a month, and help me continue helping you understand and bringing up points I find interesting about our Earth and how it all functions. Through your tips and your subscriptions, I can further this and continue to spend time building what we're doing here on Joe Slick. Joe Slick is just an arbitrary name, meaning I'm no better than anybody else, but I'm interested in this stuff, and I bring out things that interest me, and we do it live, like real Bill O'Reilly, right? Do it live. And if you'd like to be part of that show, go twitch.tv/Joe Slick Live. We are on at 7 a.m. and we do the morning report right now, like we're doing now, at 8 a.m. 7 a.m. and 8 p.m. Where am I? I'm out of coffee. That's where I'm out of. And 8 a.m. doing the morning report, which you're watching now. And you can see these articles that I post for you, the links in chat. So all that to say is we're watching the world around you. This is the current status of the sun's X-ray flux coming toward our planet, and it's low right now. It's in the low C's. We did have an M1 flare. We classify these in B, C, M, and X. Primarily there is an A, but it's, it is what it is. And we're looking at here. So the strength of these solar sunspots are measured by scientists, and they tell us which ones are stronger, which ones are weaker, which ones are stable, which ones are unstable. 25 and 20 are very unstable, and you get a positive and a negative ions, and they slap together and they explode, creating solar flares. The KP index right now is at under 2. This is a coronal hole. That does not mean it's not hot. That just means it's an atmospheric condition where a lot of solar wind can escape. This is a smaller one. Sometimes these things are really huge, and they will send it out. And now it is above the center part of the equatorial region of the sun. It does move down and it does move up, but primarily the center of it is shooting off the top of the disk. So it doesn't really affect us. 20% chance for an X, 70% chance for an M flare. Geomagnetic storms, if they do hit, 30% will be in the mid latitudes, and high latitudes maybe 15% chance. Of those, if they do, of the 70 or 20, there's another percentage chance that that's where they'll hit. All right, hold on, I gotta take this emergency call. All right, everything is good. He's just helping out. One of my neighbors. You always help your neighbors. You always help your friends, and we take care of each other, right? That's what we do. Today is the 29th There are 2 rocks out there within 5 million miles of us. And one is a 90-footer and one is, looks like a 78-footer. And the 90-footer is about 4 million miles away. The other one is just under 2 million miles away. These are potentially hazardous asteroids and other asteroids that could, affect rockets that going from here to Mars or mainly most of these are within that range, Mars range distance. And there are other potentially hazardous asteroids out there, 2,349 that are actually being watched every day, every moment of every day. And they still discover new ones all the time. And there are ones they never see that zoom in our atmosphere and come out and go, what was that? It's kind of hard to look at rock if it's not reflecting sunlight. You're looking out into space, it's dark, right? And you're looking into the sun, it's bright. So anything between the sun and us, we can really see because it blocks out that light. But when you're looking out into space, it's really hard to see something unless it's reflecting the sunlight to a point where we can see it, right? Now, big giant one we might see. But anyway, all that to say is there's a lot of things we keep an eye on. Planet positions currently, if you're looking for Uranus, it's out there. Yeah, it's on the other side of the sun. Everything is on the other side of the sun, even Pluto and Jupiter, on the opposite side of the Earth. Only Make, and Waimea are on the side of us. Kind of odd. Kind of weird, eh? We're all alone, baby. All alone with all the rocks. We had a meteor, right, that traveled right between us and the sun here last week. We watched that. That was far out, man. Yeah, that was cool. And it was in our visual range, too. So I was like, wow. Right. So looking at the buoys, these are the waters, right, that we watch around the Earth. And I call them the drunk Chinaman syndrome because the drunk Chinaman always tells us where they are. And they are quiet because they're planning to invade Taiwan. And ain't nothing we're going to do about it. But we're always watching. Remember I talk about the waves, the harmonics of the waves and all that stuff like I'm talking about. This is another tool we watch. What's going on when an earthquake happens, a large earthquake. Sometimes these instruments pick up on it and they warn us of oncoming or incoming tsunami. In addition to that, we look into the ground and we look at where the hell is it? Oh, the tremors, specifically in the Pacific Northwest. And we look at how many. There were 54 tremors yesterday, right here in Eugene, Oregon. Well, why do we look at that? Well, I told you when we look at the earthquakes, right? Zooming on out. Here's Eugene, Oregon. See this red line? This is a subduction zone where this over here is going underneath North America as it overrides it, right? So there are parts of this just doesn't disappear right here. What happens is this is going underneath. And so, the internal portion of this plate is out here by the Rockies. So it's diving down. As it dives down, some 1,000 kilometers, maybe even more, beneath North America. That's how far it goes down, thereabouts. And the vibrations of that slide can now be watched or seen by the Pacific Northwest specifically, because they put down the instruments to be able to see these things. So when we're looking, we'll see, hey, there's a grouping of vibrations that took place yesterday right there. Now, in addition to that, we got a tremor log of events that took place in the spring of 2018, day 10 of interesting. We can see patterns that persist, right? of these vibrations along the subduction zone that's offshore and the subducting plate, meaning it's going underneath North America and lifting up North America along the coast. And those vibrations are going underneath. We can see these type of events happening. And here's of 2014. We can see on Vancouver Island, it was doing it. And here's November 10th and December 10th, November 3rd to December 23rd, the vibrations that took place. And we can see it was primarily starting here and it moseyed down south, didn't it, all the way to December 10, right? So often we'll see it start down here, mosey on a way up. But in 2014, that's the direction of those events that took place. Event of last 2 years ago, 2014 or 2024, we can see when it took place here, August 6th and then September 6th. So the first month it was down here and it moved north. And that, again, is the underlying plate, the vibrating as the North American plate goes over the plate boundaries, right? As North America rides up and over. This region is where all the volcanoes are. You got Mount St. Helens, Mount Rainier, Mount Hood, and the like, right? Those are created by this plate diving underneath and this plate riding up and over. The water that's associated with the subducting plate turns into steam, it turns into gas, it expands, and as it does, it breaks the rocks. And as it breaks the rocks, it begins to melt the rocks because it gets so hot as it further it goes down toward the core. And then as that stuff rises to the surface, because it's not as dense anymore, the magma and the steam and gases that are created from all of that get trapped down, the micro gases all kind of add together. That stuff rises to the surface, creating volcanoes. And that's kind of how it works. So we're watching earthquakes here on North America right now. These are 2.5 and above. We can see along the Wasatch Mountains here several earthquakes that are starting to be visualized now. Small ones and medium ones. Mainly these are all small. Medium ones here, as the Wasatch Fault moves into Nevada, it encounters the two lineaments, remember electromagnetic lineaments, right? Of earthquakes moving down the Texas lineament, which comes out down here toward Corpus Christi, and the Walker Lane, which goes into the California shear zone inside of Panamint Valley, Death Valley, and the Owens Valley, ends up into the Mojave Desert, where I live, and continues, for some of us, continues beyond the Mojave Desert and goes down the coastal ranges of the Sierra Madre Occidental and all the way down the coastal ranges. So it meanders along the plate boundaries or the mountain ranges that exist down all the way down. So what we're seeing right now is some activity along the Texas lineament, which is coming out of here's Corpus Christi, coming out south of San Antonio, moving up through the Russell Badlands and of Texas, and then up through the Mongolian Rim, up through Arizona, into Nevada, which Nevada, the greater Nevada, is bouncing around right now with a couple of 3.2s, and I think there's another one here, a 4.4 that took place. And we look at what's going on, what the USGS has said about it. This is identified as a potential main shock of an earthquake sequence that's taken place. There are 6. This here moment tensor is telling us that's a strike slip. That means it's along a fault where one side has slid along the other side, right? And we can see it's probably a northwest to southeast trend rather than a northeast to southwest trend. Northwest to southeast trend that's happening. So only reason I would say that is because of the fault systems that are associated out here. I could be wrong, but let me look at U.S. faults. Here we go. It may happen on this fault here, the Maynard fault line that works this way. That would mean it was on the northeast to southwest, or because of the trend that I'm seeing here, northwest to southeast trend right now. Now you see another one, northeast to southwest trend as well. What would break something in the same geometry, right? This is strike slip. So this side slipped up, this side slipped down. This side slipped up, this side slipped down, right? This side slipped up, this side slipped down, right? Same thing here. Side slipped up, this side slipped down. This side slipped up, this side slipped down. What's happening? Well, it's the connection between the North American plate and the Pacific plate grinding along each other, taking and building mountain ranges, much like the Sierra Nevadas and the coastal ranges, or even the Wasatch Mountains that did that some 40 million years ago. And all the Great Basin, there's greater information that'll be said about that. I'm not going to continue into that, but how the Great Basin was created, the Grand Canyon being part of it, all these signals of events that take place, creating the topography that we all know here in the West, and how they're all created. So we're watching what's happening in California. Interesting that we've got some breakage across the Coalinga area, reminiscent of ancient days. What is this? Nacimiento, California. That's pretty close to Sister, so she's in Paso Robles area, region. Here's San Luis Obispo, right here's Atascadero, here's Paso Robles. Wonderful, wonderful area. And you see how almost in a straight line right there, bang, bang, bang. The San Andreas works its way right through the middle of this. As you see, these two are off the San Andreas, and then we're moving up north. This here is a volcano, a shield volcano, which they pump into the ground. They pump water in and create steam, and that water is made with a lot of poo-poo, liquid poo-poo, and creating steam, and thus they make electricity. That's not the only place that happens in the world. It happens down here in Southern California as well, right here also, and right here in Mexico. So we often do that, have that technology creating electricity for the world. This area is still active. We've been watching this for several weeks. Here's another 3.4 that popped off. Now, if I'm incorrect, okay, we're in terrain. These series of earthquakes, I need to look at the satellite. Yeah, still in the same area where they began, have migrated south. So a northeast to southwest trend has taken place on this. Now they've renamed these quakes to be Silver Springs. Silver Springs is right out here, the largest city in the area. They had named these things something else. I can show you by looking at all over the U.S. the last 30 days. You can see just in this area alone how many earthquakes have taken place. And I will tell you, 407 earthquakes right here for the last 30 days. Primarily right now they're happening in the southern portion, although the northern portion is still breaking up. You see here's one here and here, right? And you can see the orange ones are the most current. The yellow ones are the next couple of days, and then the white ones for the last 30 days. This is not due to one big giant quake, which happened right up here, a 5.7. But it is in a sequence of quakes. a 5.7 creating some 414 earthquakes? Could be, but everything adjusting because of this. Or is there a greater system that's going on? That's my contention. That's why when I look at these things, I say, right? So these are the last 30 days. You can see in California, Central California, that's primarily along the San Andreas. Then it comes off the Calaveras Fault and it splits into two, comes back on the Macama Fault up in the middle, then goes out to sea where Petrolia is and the like. Petrolia and Eureka are right here. This is the Mendocino Ridge that comes in here. This is a microplate now because they think it acts differently than up here. This is the what do you call it? Blanco fracture zone right here. That fracture zone to me is the beginning of the Texas liniment. It kind of migrates down out behind the Sierra Nevadas and continues all the way out down here and out Corpus Christi. This is a liniment. It's an electromagnetic liniment that continues to go all the way out and out here beyond Ascension and beyond. The Walker Lane, for some contentions, comes off of somewhere up here and then translates all the way down the coast. As the salinity of the ocean has positives and negative ions, so too do rocks and the content of the rocks. We've been studying a little bit about over the past 5-6 years about serpentine rocks and why do earthquakes happen along the serpentinite zones and fires happen. Yeah, forest fires, they just happen. Dry lightning, they just happen. There's no cloud in the sky, yet there's lightning. A lot more to our planet that exists that many people don't bother to research and look up because it's boring, right? It's just a mountain. Well, how'd that mountain get created? So I love raw garlic too. I eat that. That's really good stuff. Off the shore of Chiniak, Alaska, there was a 4.2 that took place yesterday. Okay, off of Japan, still, they are waiting for a very, very, very large earthquake to take place, and it could happen in next year. Remember, geology time is not the same as mankind time. We have a smaller, limited window of life itself. The Earth has been around a lot longer than man. So we have a 4.4 off Japan. At the same time, we have the Philippines along this plate boundary, a 4.9 and a 4.4 down north of Halmahera, and this is over by Manam volcano. Could be, eh? And we'll talk about volcanoes in just a minute. China talked about these two earthquakes already, 4.6 and a 4.8. There seems to be some sort of trend line that works its way up and around this way. In addition, it works its way down through this way. Also, off of Japan, works its way through the Amur plate. Remember? I can show you. Right? Here's the one way, and then here's the other way. The Yangtze, the Amur plate, right? Coming over to the Eurasian plate, which is all of it. It depends on just how connected things are. Then it works through the stands. This is kind of the flow of earthquakes. It works through the stands all the way to Uranistan, and then it works into the women, which is Iraq, Armenia, Georgia, Azerbaijan. These are kind of funny things that I say, and I call them the women of the area, names of the countries. Then it gets into Turkey, and as it gets into Turkey, then it's affected by the African plate pushing up and underneath the Eurasian plate here. We often see Turkish earthquakes move out towards Cyprus, then up into Greece, which Greece is all this area right here, part of real close to the islands off of Turkey, tell you the truth. And we've seen Crete being popped off really well. If I did that, you can see there's a whole cluster of them right there that took place. Nothing is happening today thus far on the USGS. That doesn't mean it's not happening. They just didn't report it. And then as it works through itself, Greece, often we'll see it bounce over here through Italy and then into Spain and then out into the mid-Atlantic. And then from there, that energy is pushed through North America again as it continues to rotate around the planet. As it does, it comes through the Caribbean plate, moves south into the South American plate along that boundary, and often we see a motion out of Kamchatka, where the plate is actually going underneath. The Pacific plate's actually moving this line here, that the Hawaiian seamount chain. That's the direction of the Pacific plate, moving right into Japan. It used to move in a more northern direction, but it doesn't now. It moves more than that direction. As it does, we can see along the ring of fire, so to speak, plate activity move from Kamchatka to Tokyo through the Philippines, Halmahera, into PNG, into Vanuatu, into Fiji, and the Tonga, and New Zealand, and migrate around the plate boundary and end up influencing quakes in North America as well as quakes in Central America and in South America. So the flow of quakes happens, and it's real. Can we say what's going to happen? No, but we can see it happening, and we can say, okay, that's related to something here, the plate movement. If we can diagnose how the plate's actually moving at moment, that would be far friggin' out, and then would we be coming closer to forecasting. Now, another aspect, we just had an earthquake down here in the Prince Edward Islands below Africa, and that is the Texas liniment, and it goes out here to what I call Caligula. So Prince Edward had a couple of bangers, 3 5s, bang, 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 bang. All three right there, boom, 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 boom. Very, very strong movement. Man, I'm being paged all day long, am I? I'm not 10 o'clock yet. Man, I should shut my phone off, but I don't. Anyway, so looking at that, then we should also look at volcanoes. Why? Volcanoes release energy that's down below. So unrest in Costa Rica, Poas and Rincon de la Vieja, and Turrialba is all at yellow. So Central America is really banging off. There's a plate down there that's a Panamanian plate that connects to Costa Rica. 3 volcanoes are active, and they've been popping for a while. They're just saying now they're all upgraded to yellow. So today in the news, April 29, 2026, Santa Guido, Fuego, Popo, Simiru, Ibu, Ducono, Rincon de la Vieja, and Reventador. So Sebencaya, hey, knock that off. Sebencaya, down in the armpit of South America, right? Well, what's the armpit of South America? Well, if you look down here, this is the armpit, and that volcano is roughly right there. All right, cool. So 26,000, it's a 19,000 foot volcano going to 26. Reventador, 11,000 going to 16,000. That's in Ecuador. That's up here, right? Here's Colombia, here's Ecuador, here's Peru, right? Reventador is like right out here. And the other one, Sangay, is down here. So We're looking at them both all the time. Dacono, 8,000 foot out of Dacono. Now it's a 3,800 foot mountain. And then we zoom back out over here in Indonesia, at the bottom down here where this earthquake took place. This is Halamarahara. I know I added consonant. Deal with it. Dacono and Ibu both here, been popping for better part of a year, year and a half, with steady explosions. Sometimes they get rather high, a mile high or 2 miles high, 3 miles high, telling you that there is great movement happening along the Pacific, where right here is the Philippine plate, and where the Pacific plate, the Philippine plate, and all of these other little microplates all come together and get pushed up, and then the closing of this gap between the Celeb Sea and the Halimara area is closing in, and there's actually a plate in here that's no longer, because it's below the surface of the ocean and it's disappearing. So this is coming into this, and this is coming into that, and this is the Malacca Sea, right? We've seen often big earthquakes in this region. We had a 7.4 here this year, right out here. Mm-hmm. And then the movement of all this area. Understanding the earthquakes, you've got to understand how this the complexity of the movement of each of these little microplates happens, and then we see where the trend is going on, and that's the like. Now, volcanoes are talking to us about how much pressure is below being ushered up into the surface. So Fuego volcano, 14,000. It's been a little bit less. Normal Fuego is about 15,000. It's a 12,003 foot mountain in Guatemala. Now, Guatemala City right here, Fuego's right here, and then we have another one which is up here, Santa Maria, which is also Santa Guido. 50 miles apart. Those two volcanoes are popping off primarily all the time. Both are about 12.3. Santa Guido's a lesser volcano. It's a new volcanic event that has taken place after Santa Maria exploded in a VEI 3, I think, or maybe a 6. That's how they measure the explosivity of a volcano, and it happened in late, early 20th century. Late 19th, early 20th century. So as a result, Santa Guido has emerged from that area. Taal volcano, a super volcano there in the Philippines, is putting out 3,000 feet. Zooming out again, going over here to the Philippines. And Taal volcano, just south of Manila. Taal volcano is right there. You can see the big circle of it. Yeah. Last, I don't know, about 3 years ago, this thing erupted, right? And its eruption was really a steam eruption. And it, from what I read, it melted, or it steamed off all of this water. The water has come back, all right? And it seeped back in, and so the lake exists again. This is the caldera of the entire Taal. It is a super volcano. When we're watching this happen here, I'm watching out here, seeing what earthquakes are happening along this area. It seems to me that when this was active, this portion of the plate was active. Now, that fault system works all the way through and back onto this level. And we did have a 7 out here. We do have Canloan volcano that's active here. We do have, I think it's, it might be up here, or it might be right here. Another volcano from the Philippines. Well, there's Ibu, so Ibu and Dacono are still popping away. Santa Guido, I was just telling you about that. It's popping. Poas, Rincon de Viejo, hold at yellow as unrest spans in Costa Rica continues. Mayon is the other volcano that's there in the Philippines, 9,000. It's not a very big mountain, so how we look at it is as 8,000 foot mountain. We subtract the number that I gave you, 9,000, and that would tell you that it's an eruption of about 1,000 foot. Meaning you don't fly a plane below that level. So the safety zone is above. So you can be pumping 500 feet, but they want to give you that buffer. Sakurajima volcano, 6,000 feet. That's in Japan, the southern portion of Japan, moving up the coast. It's another super volcano that's out here. I believe it's a super volcano, Awu, and Sakurajima is right here. It erupts often. Yeah. And there's another super volcano that it's infilling right now. Japan has released documentation to say this down here is infilling. Now we have Suonozajima, which is down here. It's not in the news, but it's constantly erupting as well. So all of these volcanoes are erupting. I think all of them kind of go to here. Then it's kind of quiet. Then as we get over toward the plate boundary here between the North American plate and the Eurasian plate, volcanoes are active on both sides here. And Fuji is part of this down here, part of this mess down here. So that's to give you a little focus on what's going on. Reventador there in Ecuador, 15,011 and change. Fuego, 14, and that's still, well within its normality of a 12,003. So do the subtraction and you'll find out how much. Popo there in Mexico City, Popocatépetl, 20,000 feet. Now it's a 17 and change, so 17.8, 17.6. And I can tell you what they quoted at now. 17.8. 17.8. So when it's going 17.8, going to 20, you can do the math. It's roughly 3,000 feet, right? Or 2,000 feet, right? Sebankaya, that's over there in South America, the armpit, still erupting. 19,000 and change foot mountain going to 25, 26, so it's crazy. Sangay, 22,000 feet out of a 17 there in Ecuador. Again, what did we say Ecuador was? Down here. There's Ecuador. Sangay is down this region here. Semeru, they're in Indonesia, the largest active volcano in Indonesia. They're saying that it's erupting, but we can't see it because of it's ground. We're on the ground. We can hear the damn thing going off, and it's scaring the piss out of us. But we can't see it. So boom, it blows up, and there's Semeru right there. This is the Java, the southern Java. Here's Bali, right? We have also down the way several other volcanoes that aren't, erupting at the moment, but we do have two volcanoes over here, Little Toby and Little Tolo, both popping away constantly over the last year or so, year and a half, talking to us about this plate boundary, that it's super active. And we've had a 7.6 that happened out here maybe 3 years ago. And as a result, Timor region is always banging away. And these volcanoes haven't stopped since. And Sulawesi, we've had a lot of earthquakes along the Sulawesi and Malacca Sea there. We've had to ban the sea. Several large earthquakes coming out of the Flores Sea over the last 6 years. And then over here, the Java Sea as well. And then we haven't seen really any big quakes along this region. Now, this is one of the most active subduction zones in the world. Now, you remember back in 2014, 2011? I always get mixed up. Maybe 2004, I don't remember. The big earthquake that took place out here, that Banda Aceh and Phuket got all wiped out in the Andaman Sea here because of what? Tsunamis, right? A tsunami was created. It bounced off of Sri Lanka. It bounced off of India. It came right back and hit them again. So we got the first one, the second one, the third one, the fourth one. Keep pounding back and forth because like a fishbowl, the Bay of Bengal kept doing it. These things were, big waves but it's the entire ocean rose and went inland, much like it did Japan in what 2011, 2014. I don't remember. I get both of these mixed up, the dates. That northern part of Japan, how we've often see one happened in 2004, one happened in 2011. I think this was the 11, the other one was 2004. We've seen how much the ocean can come in on a landmass that has sank because of the release of the top part going over the subducting plate. Because as this is pushed up inside, it uplifts the mountains and it uplifts the sand, and it comes out of the rising out of the water. And so people say, oh, look at this land, let's build a house. Well, when it breaks free, that ocean reclaims that part of the land. And that's what happened up in Japan. Some of it is still underwater today. Also, the tsunamis were created, and that's kind of what we always kind of watch and or in concerned about. So, and that would do it for our report today. All right. So, I appreciate you all being here. I appreciate you all listening. It's 10:07 here in the West, and I hope I gave you a little bit of more information than what we normally do, only because we haven't done a rabbit hole in a minute. I'm kind of waiting for my boy Canuck to feel better. He had eye surgery, so yeah. And so it just so happens Zelensky out there in Ukraine, as Russia is smacking Ukraine and Ukraine's beating the shit out of them. The Middle East focus, and I think that's part of the mechanism of our president, who's trying to end this war, getting these stupid fatalists, death cults to be subjugate to the whole world, which will never happen. But anyway, so the Middle East focus eases the pressure on the Russians, and the Russians are feeling it. So, yeah. And Trump is, President Trump therefore is considering extending the blockade, which I love. It's all great. Anyway, big hugs, y'all. Yeah, how did Planned Parenthood get $90 million in COVID loans? They're not even about COVID. Big hugs, y'all. Don't get none on you, and have a great day. Remember, Joe Slick Live on twitch.tv/Joe Slick Live. You can be here in the mornings, and we can do it live with you if you're over there on YouTube or on Rumble. And if you want to help out the channel, you can subscribe, and you won't get the commercials. Believe me. Twitch is always, and like everybody else, like even YouTube has commercials. But you can avoid them by subscribing. Also, you can leave a gratuity over here at Stream Elements /Joe Slick Live !TIP. Thank you, and have a great, wonderful day. Wednesday, normally we do Rabbit Hole, but I did it in the morning here for you. Big hugs, y'all, and don't get none on you.
Well, howdy there, friends. Let me introduce. I'm Joe Slick. Yeah, I'm here to produce. Citizen journalist. I'm out on the scene 24/7. I'm living the dream. Got my camera rolling, ready for the scoop. With my trusty crew, we're a wild bunch of troops. From dawn till dusk, we'll uncover it all. Rattling the truth in this media brawl. Come take a journey with me. Come ride on my train. We'll dive into the long and winding lane. Events and phenomena we're here to share. Joe Slick and the crew are going everywhere. Morning reports at 8 will break down the news. In Arizona time, we'll light up We bring you the light, unveiling the shadows, we'll put them in sight. Wednesdays and Saturdays, the rabbit hole's live at 7 p.m. where the truth will thrive. Digging deep, uncovering the lies, sifting through the chaos, we're reaching for the skies. So tune in, friends, don't you ever miss. Joe Slick's got the stories that you shouldn't dismiss. Come take a journey with me, come ride on my train. We'll dive into the long and winding lane. Events and phenomena we're here to share. Joe Slick and the crew, we're going everywhere. The weekly wrap up, Fridays at 5. Catch all the highlights, feel the vibe. So grab a front row seat, let's unravel the tale. With passion and grit, we'll never fail. We're on this mission, yeah, we're gonna shine. Join the journey, my friends, it's about that time. Remember what I say, let it stick in your head. Don't get known on you, just words that we spread. Come take a journey with me, come ride on my train. We'll dive into the long and winding lane. Events and phenomena we're here to share. Joe Slick and the crew, we're going everywhere. Morning reports at 8 will break down the news. In Arizona time, we'll light up your views. So here's my invitation, don't let it slide. Joe Slick's got the stories, come take a ride. With a wink and a smile, we'll navigate the path. Together we'll find truth, let's do the math. Citizen journalist, I take pride in my name. Joe Slick's on the mic, we're changing the game.